in my last lecture I discussed the operation of 3-pulse converter, that is 3-phase half-wave rectification. We found that each device conducts for 120 degrees and each phase is also supplying power for 120 degrees. Okay. So each phase supplies power only in half a cycle for 120 degree duration. We used 2 such bridges and we got a 3-phase full wave rectifier. Okay. And we found that there is one common cathode configuration and there is another common anode configuration. Each device conducts for 120 degrees, but then each phase supplies power for 240 degrees in a cycle, okay, provided the load current is continuous. Okay. So in other words, at any given time one phase is open, it does not supply any power to the bridge. There are only 2 devices are conducting at a time, one device in the upper half, another device in the lower half, and they do not belong to a same phase, remember. So at any given time in a 3-phase full wave rectifier, one phase is open and 2 phases are supplying power to the load. And there are totally 6 pulses per cycle, each pulse of 60 degree duration. See, remember, each device conducts for 120 degrees, but then there are 6 pulses, each of 60 degree duration. Okay. Hence the name 6-pulse converter. So we have, so far you have studied 1 pulse, 2 pulse, 3 pulse and 6-pulse converter. What are the advantages of increasing the number of pulses? I will just show you a transfer slide. This is a waveform for a half wave rectification. Okay. I am assuming either purely resistive load or maybe a half wave rectification using a freewheeling diode. Full wave rectifier, 3-pulse converter and a 6-pulse converter. I said this is a AC to DC conversion. I would like to have almost a constant value of DC voltage. So definitely I would filter this waveform to get a constant DC. Now if you compare here, in which case the filtering requirement is maximum and which case it is minimum. To have a constant DC in half wave rectification, definitely the filter requirement is the highest, because for 0 to pi the load voltage is same as the input voltage and pi to 2 pi it is 0. Now I need to have a constant DC. Okay. So definitely my filter requirement here is more, whereas in 2-pulse converter there is no 0 voltage duration, there is no period wherein output voltage is 0 here. So definitely filtering requirement reduces, but then output voltage changes from 0 to Vm. Okay. What happens in 3-pulse converter? We found that yesterday there are 3 pulses and the minimum value of V naught, it is proportional to sine 60, it is root 3 by 2 or root 3 by 2 per unit, and this is again the peak value is Vm. For alpha is equal to 0 of 3-phase half wave rectifier, the voltage, output voltage varies from root 3 by 2 to 1. What happens in 6 pulse? We discussed yesterday for alpha is equal to 0 or that is equivalent to an uncontrolled bridge. We found that this voltage changes from 1.5 per unit to root 3, that is approximately 1.7. So, in 6 pulse converter with alpha is equal to 0, the variation in the output voltage is 1.5 to 1.7. So, that is approximately a constant for an engineer. I can say that output voltage remains approximately constant. I may not require any filtering. See, therefore, as the number of pulses increases, your filtering requirement comes down. The maximum in 1 pulse converter, minimum in 6 pulse converter. 6 pulse converter we will see somewhere while doing DC to AC conversion, we'll find that filtering requirement there is minimum. In some cases you can do away with this filtering even to have a constant DC. Okay. Now, what is the expression for the average value of the output voltage? There are 6 pulses per cycle, each pulse of 60-degree duration. Alpha is measured with respect to the point of natural commutation. So, therefore, if I need to integrate from pi by 6 plus alpha to pi by 6 plus alpha to pi by 3, okay. And we found that when divide D1 or T1 and D6 or T6 are conducting, output voltage is VAB. So, the magnitude of VAB is root 3 Vm sin omega t plus 30. So, we will find if you simplify this, you will find that it is 3 root 3 by pi into Vm into cos alpha, where Vm is peak of the phase voltage. See, we have taken Vin is Vm sin omega t. This is a phasor, so it is V is the RMS value. So, if I substitute for Vm, you will get 2.54 into V into cos alpha, okay, where V is the RMS value, alpha is the trigger angle. So, this is also equal to 2 into this expression, and we found that this is the expression for output voltage of a 3 pulse converter. Okay. So, average output voltage for a 6 pulse converter is twice the 3 pulse converter. Okay. So, here is the equivalent circuit. It is 2.54 into V into cos alpha, RMS value of the phase voltage. RMS value of the phase voltage is variable because it is a function of alpha. 2 devices are conducting at a time, and here is the load voltage. This is the load voltage, the current. I told you that each device conducts for 120 degrees. So, if I find the RMS value of the source current, it is found to be root 3 by 2 into I naught. So, source, if alpha is equal to 0, phase A supplies power from pi by 6 to 5 pi by 6 in the positive half, and in the negative half it is 210 degrees to 330 degrees. So, each phase in each cycle power supplied by the source is of 120 degree duration. Okay. So if I assume the load current to be constant and ripple free, that means load current is constant of value I naught. If I find the RMS value of the current, source current, it is found to be this value, root 2 by 3 into I naught. Whereas in a single phase bridge, if I assume that load current is of constant and ripple free, RMS value of the source current is same as I naught. Whereas here it is different because each phase supplies power for 240 degrees. So if I assume a load current of constant and ripple free, source current is of a square wave of duration 120 degrees in each cycle. In a single phase case, it was a square wave of pi radians. So if I take the harmonic series, or if I write the Fourier series for a single phase bridge, we found that all the triplen harmonics are present. In other words, all odd terms are present. Sin omega t, sin 3 omega t, sin 5, 7, 9, 11, so on. All odd harmonics are present in a single phase case. Whereas in a 3-phase, 3-wire system, you cannot have triplen harmonics. I am sure this result your teacher who is teaching machines might have told you. So therefore, in a 3-phase, 3-wire system, you cannot have triplen harmonics. Okay. So if I write the Fourier series, you will find that there are only 6n plus or minus 1 harmonics. In other words, there is fundamental sin omega t, next is sin 5 omega t, sin 7 omega t, sin 11 omega t, sin 13 omega t. This is also equal to sin 6n plus or minus 1. N takes the value 1, 2, 3, so on. So in a 3-phase, 3-wire system, there are only 6n plus or minus 1 harmonics and the fundamental. So harmonic content is also reduced in a 3-phase. There are no triplen harmonics. The frequency of the harmonics present in a 3-phase, 3-wire system also increases. What implication it has, we will see sometime later. Okay. Yesterday we discussed for alpha is equal to 0. Today we will study the waveform for alpha is equal to 30 degrees. Okay. Alpha is measured with respect to the point of natural commutation. So T1 is the reference for thyristor T1, this is the reference point. T3, this is the reference point. T5, this is the reference point, while device that is connected, that is 2, this is the reference point. 4, this is the reference point, and this is for T6. See, B phase is getting negative. So at alpha is equal to 30, this is alpha is 0, alpha is 30, T1 is triggered, G1 is getting a tree pulse. So prior to point P, T6 was conducting. At P, P is the reference point for 2. So prior to 2, 6 would conduct in the lower half. So 6 was conducting. Now what is the output voltage? When T1 starts conducting, the positive DC bus or potential of X is VAN and potential of Y is VBN. Okay, refer the bridge which we have drawn it yesterday. Okay, so VIN is proportional to sine 60. Mind you, alpha is measured with respect to this point, but then we need to find out the instantaneous value of the phase, the corresponding phase with respect to its zero crossing. Okay, so at alpha is equal to 30, instantaneous value of VIN is proportional to sine 60. Okay, that is root 3 by 2, and VBN, it is sine 300. Sine 300, 6 was conducting, so it is minus root 3 by 2. So therefore the peak is, therefore the value of the output voltage VO is VIN minus VBN is found to be root 3. So with alpha is equal to 0, the peak value of the output voltage is root 3. So even at alpha is equal to 30, the peak value of V0 is still root 3. Now let us say after 30 degrees what happens. So we are somewhere at this point, that is P, we will find that A phase is at the peak, that is sine 90, 6 is still conducting, so instantaneous value of phase B is sine 330, that is minus half, so output voltage is 1.5. Output voltage is 1.5. This is corresponds to 1.5. Now 30 degrees beyond P, T2 is getting triggered. Let us see the output voltage just prior to triggering 2. Okay. At that instant, VIN is proportional to sine 120, or say 120 minus, that is still root 3 by 2. VBN is approaching 0, maybe 360 minus, therefore it is 0. So the load voltage is VIN minus VBN, it is proportional to root 3 by 2 itself. So just prior to triggering T2, output voltage is root 3 by 2. The moment you trigger T2, now the load voltage is VIN minus VCN, because T2 starts conducting, T2 is connected to phase C, so the load voltage is VIN minus VCN. Instantaneous value of VCN is proportional to sine 60 or sine 240, okay, that is again minus root 3 by 2. VIN is 120, again it is root 3 by 2. Output voltage is VIN minus VCN, so output voltage jumps to root 3 by 2, minus of minus root 3 by 2, it is root 3 itself. So peak value of the output voltage even with alpha is equal to 30 degrees is root 3, but then the minimum value is reducing, it is now root 3 by 2, and now moreover there is a sudden jump root 3 by 2 to root 3, because at this instant you are triggering another device, incoming device, okay. So from in this instant T6 and T1 are conducting, and T1 and T2 and so on. I encourage you to draw the remaining 6 pulses also, okay. Now what is the effect of increasing alpha on the power factor or the duration or the instant at which the source supplying power? Phase A voltage is becoming positive here, okay, there is a positive zero crossing. If alpha is equal to 0, it would have started supplying the current from this instant, okay. I cannot reduce this period beyond this, okay. So alpha is 0 is here, so it can, the phase A can start conducting only at alpha is only at omega t is equal to 30 degrees. Now I am triggering at omega t is alpha is equal to 30 degrees, that is omega t is equal to 60. So phase A is open till omega t is equal to pi by 3 radians, okay. So the positive crossing of the source current can be at this instant. If alpha is equal to 0, the positive crossing could have been somewhere here. Now with alpha is equal to 60 degrees, the positive crossing becomes here. In other words, I am delaying the current. In other words, source current started becoming more and more lagging, okay. If alpha is equal to 0, the zero crossing of the source current would have been here, now it is here. So this angle is increasing, the angle between the positive zero crossing of the voltage and the positive zero crossing of the source current is increasing. In other words, power factor is deteriorating. Remember, as you increase alpha, power factor deteriorates, okay. Okay. Now let us see what happens with alpha is equal to 60 degrees. At this instant, T1 is triggered, okay. Prior to T1 or prior to triggering T1, T5 was conducting, okay. In the lower half, in this instant, T6 is conducting, okay. So what is output voltage just prior to triggering T1? It is VCN, because 5 is conducting, minus VBN, 6 is conducting in the lower half, upper half 5 is conducting. So VCN minus VBN, okay. What is VCN? VCN is 210, proportional to 210 degrees, that is minus half. VBN, it is 330 degrees, it is again minus half. So output voltage is VCN minus VBN, it is 0. So now it is touching 0. Whereas in the both the cases with alpha is equal to 0 and alpha is equal to 30 degrees, it did not touch the x axis. Now with 0, with x alpha is equal to 60 degrees, is just touching the x axis, okay. Now at point P or at this instant you have triggered T1, now output voltage becomes VAN minus VBN. What is VAN at this instant? Proportional to sine 90, sine 90, it is 1, okay. Whereas VBN is still at 330 plus, okay. So it's again minus half, minus half. So VO is 1.5 times the peak value, or 1.5 per unit. See the difference now. For alpha is equal to 0 to 30, we had still the peak value of root 3. So alpha increased above 30 degrees, the peak value comes down, peak value comes down. Now with alpha is equal to 60 degrees, we found that peak value is 1.5, minimum is touching 0 now. Now what happens to the output voltage waveform beyond 30 degrees from there? At this instant, VAN is sine 120, that is root 3 by 2. we haven't triggered T2, 6 is still conducting, so VBN at this instant is 0, so output voltage is root 3 by 2 itself. VIN minus VBN, VBN is 0, so it is root 3 by 2. And what is the output voltage just prior to triggering T2? It is same as the output voltage just prior to triggering T1. Okay, whatever that happened to T1, it will happen to T2 also, maybe in the lower half. So you will find that output voltage is just touching 0. The moment you trigger T2, output voltage jumps to 1.5. Okay. So output voltage here varies from 1.5 to 0. Now it is touching 0 with alpha is equal to 60 degrees. Okay. So here is the procedure. I would expect you to continue the remaining 4 pulses also. Now let us see what happens with alpha is equal to 90 degrees. Corresponding value of omega t is 120. Okay. VIN is root 3 by 2, bottom of 6 is conducting, VBN is sin 60, it is 0. So V naught is root 3 by 2. Okay, the moment I trigger T1, it jumps to root 3 by 2. Okay. What happens after 30 degrees? At this instant, VIN is sin 150, that is half, and VBN is sin 30, it has become positive. Okay. So instantaneous value of VIN is same as instantaneous value of VBN. So output voltage is 0. Okay. Now what is output voltage just prior to triggering T2? Okay. VIN is maybe 180 minus, it's approximately equal to 0. VBN is sin 60 minus, it is approximately root 3 by 2 itself. So VIN is 0, VBN is plus root 3 by 2, so therefore output voltage is VIN minus VBN, it is minus root 3 by 2. So therefore for alpha is equal to 0, output voltage varies from root 3 by 2 to minus root 3 by 2, provided the current is continuous. Remember, provided the current is continuous, output voltage when alpha is equal to 0 varies from root 3 by 2 to minus root 3 by 2. So if I summarize the 3 waveforms, you can have a peak value of root 3 till alpha is equal to 30 degrees. So anywhere from 0 to 30, peak value of the output voltage is the same. For alpha less than 60, V naught is always positive. At 60 degrees, V naught, the instantaneous value of minimum value of V naught becomes 0. And if I increase alpha beyond 60 degrees, minimum value of V naught now starts becoming negative. Okay, it becomes negative. So if I ask a question, if the load is purely resistive, so what will be the instant, or what should be the trigger value of alpha beyond which current becomes discontinuous? Definitely it is 60 degrees, because at 60 degrees the minimum value of V naught is 0, that is the voltage appearing across the resistor, current also will become 0. So current is just continuous if in the case of a resistive load for alpha is equal to 60 degrees. Above 60 degrees, current becomes discontinuous. Current becomes discontinuous. And mind you, you cannot use the expression 2.54 into Vm into cos alpha if the current is discontinuous. That is valid only if the current is continuous. Alpha is equal to 90 degrees, we found that average value becomes 0. What sort of a load we are talking about? What sort of a load we are talking about? Or in which case average value of the output voltage is 0, but the current is continuous. It can happen only if the load is purely inductive, because average voltage across the inductor is 0. Okay. So what happens is, in this waveform, this is positive L di by dt and this is negative L di by dt. Current starts from 0, reaches a peak here, because at this instant L di by dt is 0, so current has to be peak and again comes down and becomes 0. It's just continuous, just at the boundary between continuous and discontinuous. For other loads, you cannot have a continuous conduction for alpha is equal to 90. For anywhere, for even if the load is of RLE type, I into R is always positive, E is positive, E is positive. So average value you cannot have, average value across the inductor is 0, so Ri plus E should be 0, it's just not possible. Okay. So load current can be continuous for alpha is equal to 90, so only for an inductive load, purely L load. Okay. Last case, I will just increase alpha is equal to 120. Okay. Okay, alpha is equal to 120. Now corresponding omega t is equal to 150. Okay. So VIN is proportional to sin 150, that is half. Beyond, in the lower half, T6 is conducting, because we haven't triggered 2 is triggered somewhere at this instant. Okay. So 6 is conducting, the potential of Y is VBN and potential of X is VIN. Instantaneous value of VIN is same as instantaneous value of VBN, so output voltage is 0. VBN is sin 30 and VIN is sin 150, output voltage is 0. Let us see what happens beyond 30 degrees, beyond from this point. VIN is sin 180, 0. VBN is proportional to sin 60, that is root 3 by 2. Output voltage is VIN minus VBN. Okay. It is minus root 3 by 2, minus root 3 by 2. And what is output voltage just prior to triggering T2? Just prior to triggering T2, output voltage is still VIN minus VBN. VIN has become negative, it is sin 210 minus also, and VBN is sin 90 minus, sin 90 minus. So VBN is minus 1 approximately, VIN is minus half, so output voltage is minus 1.5, minus 1.5. This peak is minus 1.5, minus 1.5. Okay. So at this point T2 is triggered. Now the moment T2 is triggered, now output voltage is VAN minus VCN, sorry 462 VCN, right, VCN. Okay. instantaneously this voltage becomes 0. Instantaneously voltage becomes 0 at this point, because AN is 210, CN is 330, so both are minus half. So minus half is plus half, it is 0. So for alpha is equal to 120 degrees, if I summarize, it becomes 0 and always negative. Whatever that happened for alpha is equal to 60 degrees. Alpha is equal to 60 degrees, we found that instantaneous value or minimum value of V naught is 0 and it is positive. Okay. So at alpha is equal to 120 degrees, it is 0 and negative. Okay. Just the opposite. These are the two pulses. See, we have triggered T1 at this instant. The positive value, the positive zero crossing of the current is somewhere here. Positive crossing of the phase here voltage is somewhere here. So this angle goes on increasing. Power factor deteriorates with increase in alpha. Okay. I am not going to do for alpha is equal to 150 and alpha is equal to 180. Same procedure, you follow it and you will find that whatever that happened for 30 degrees, it will happen for alpha is equal to 150 but negative. Whatever that happened for alpha is equal to 0, it will happen for alpha is equal to 180. Okay. So far we drew the waveforms for alpha is equal to 0, 30, 60, 90 and 120. Suppose now that you have to go to the lab, you have been given a 3-phase bridge, there is a load. Now what value of alpha will you choose? Now forget about 3-phase, now let us talk about single phase, relatively easier. Say assume that you have a DC motor as a load, RLE type load, DC motor. Motor is station in the sense rotor is not rotating. What will you choose the alpha to be? In our machines lecture, our teacher has told that you need to apply reduced voltage to the DC machine, full field reduced armature voltage, so that the current drawn with the motor reduces, also it accelerates faster, because when the motor is at standstill, back EMF is 0, the current is limited by the armature resistance itself. Invariably students say that we should choose alpha is 90 degrees if a single phase fully controlled bridge is feeding a DC motor. Why? Because if alpha is equal to 90 degrees, average value is 0. So alpha is equal to, I am applying a very small voltage, or in fact 0 voltage, and go on reducing alpha. Now my question is, can we start at alpha is equal to 90 degrees? Answer is simply no. Why? See the waveform here. The input AC, RLE is a load, E is 0. Say inductance is very small here. I am assuming that there is no a filtering inductor in the DC side. Of course things do change if there is a filtering inductor here. Okay. Now the current is limited by R itself, a small, which is very small. Armature resistance is very small for a motor. Again, armature inductance is also very small. Prior to triggering these devices, there was no current. So if you trigger the bridge at alpha is equal to 90, the instantaneous value of Vn is Vm, is at the peak value. So your peak voltage you are applying to the motor terminals. If it is 230, you will get around 320 or so. 320 volts, current is limited by R and a small l. It will so happen that a large current will flow and may damage these devices. So therefore, a safe value may be towards 150 to 160. It all depends on the parameters of the machine or the DC side. If I have an inductor, of course you can decrease this value. Otherwise, maybe start somewhere near this point and reduce alpha towards 90 degrees. Now, please don't say that, sir, you are triggering at 150, average value is negative. Yeah, average value becomes negative beyond 90 degrees only if the current is continuous. You haven't even established the current in the circuit. So the question of current being continuous doesn't arise. Okay. So depending upon the value of R, L, E, current builds up and it may become 0, because if you keep the same alpha it may become 0 much before that. So if you want to accelerate the motor, you go on, reduce the alpha towards 0. Okay. What happens for a 3-phase case? Things are not very straightforward here. Why? At any given time, two devices are conducting. Changeover from one device to another device, one device in the top and one device in the bottom, they do not take place at the same time. So changeover from T5 to T1 takes place at some omega t. After 60 degrees, changeover from 6 to 2 takes place. Okay. The second is, at any given time two devices should be on. There is no current, you haven't even established any current in the bridge. You have put on the AC supply. To establish the current in the bridge, two devices have to be triggered. So your pulse patterns should be such that two devices or any pair, T1, T2, T2, T3, T4, T4 or whatever, should get trigger pulse simultaneously. Okay. So all the waveforms that I have drawn so far, I have just shown you only one pulse. In that scheme may work at steady state provided the current is continuous. I will repeat, I have shown you only one pulse in the gate circuit. That may work at steady state provided the current is continuous. Okay. So while starting, or if the current has become 0 in between, to re-establish the current in the bridge, two of them again should be triggered at the same time. Okay. So the pulse pattern should be something like this. Something like this. T6, T1, T1, T2, T2, T3. So I need to have two pulses are separated by 60 degrees. Okay. See here, 6 and 1 are triggered at the same time. Now 6 also may be triggered at the same instant, but then the moment you trigger 2, say after 120 degrees also, from here 6 will turn off and 2 will come. Okay, 2 will come. So at any given instant, two devices should be triggered simultaneously. Okay. By the way, this pulse should be shown. This is an ideal case. Please don't think that just because we are triggering again here, 6 will continue to conduct for another 120 degrees. No. See, you are triggering 2 after 60 degrees. See, this duration is 60 degrees. So the moment you trigger 2 somewhere here, 6 turns off and 2 starts conducting. Okay. So ideally you need to have 2 pulses which are separated by 60 degrees. In a single phase case, we found that if the load is of RLE type, current may become discontinuous. You have triggered the bridge T1 and T2 in the positive half, they started carrying the current. Now E is higher than the instantaneous value of Vi. In that case we found that di by dt is negative, and it may so happen that current may become 0. Please recall, I have discussed all this. So therefore we said that instead of having a one pulse, have a series of pulses. Same concept is still valid in 3-phase case, because if the load is highly inductive, we know that gate signal should be present till the current through the device is higher than the latching current. So gate signal should be present. We know that if the load is highly inductive, current cannot change instantaneously, or current slowly builds up. So if there is only a sharp pulse, by the time Ig becomes 0, current won't have increased to is the latching current. So SCR T1 turn on. So generally a series of pulses of duration 70 to 75 degrees is used. Okay, I might have said that theoretically 2 pulses of 60 degree duration, 2 pulses which are separated by 60 degrees are required. The general practice is have a series of pulses of the total period is of the order of 70 degrees or so is used. Okay. By the way, what is the maximum value of alpha to start the bridge in a 3-phase case? We found that for alpha is equal to 120 degrees, minimum value of V0, in other words V0 touches 0 and becomes negative, it does not become positive at all. Okay. I have not even established the current in the circuit, let it be whatever may be the type of load, we have not established the current in the circuit. To establish the current, I need to have a positive voltage across it. If alpha is equal to 120 degrees, it is either 0 or negative. So you can't establish any current in the circuit. So therefore, in a 3-phase bridge, the maximum value of alpha to start the bridge is or should be less than 120 degrees. It is only then a positive voltage appears across the load. For alpha less than 120 degrees, for a small duration, a positive voltage appears across it. If the positive voltage appears across the load, current starts flowing, current builds up, yes, then you can go on reducing alpha depending upon the load requirement. Okay. So alpha max should be less than 120 degrees, should be 120 degrees, so that a positive voltage appears across the load, and ice starts flowing. Okay. Again, I am assuming here that load is passive. Things will change if I have a battery there. Okay. Things do change. So if the load is a passive, alpha max should be less than 120 degrees. 120 degrees. So here is the sequence. A series of high frequency pulses of 70 to 75 degrees, and see, there is an overlap here. This is the overlap. This duration, this is the overlap. 1 and 6 are triggering at this point, or this is the instant where G1 should be triggered. So at that instant G6 still have few pulses, because even if the current has become 0 somewhere, this at this instant G1 is also started conducting. G6, sorry, at this instant G1 is getting a trigger pulse, and there is a trigger pulse for 6 also. So current you can establish in the circuit. Okay. So far so good. All this analysis we discussed for source inductance 0. We have neglected the source inductance. So that is why current changes instantaneously from 0 to the value of load current the moment you trigger the thyristor. And if I consider a finite source inductance, instantaneous change is not possible. And in the single phase case, we found that during commutation period, output voltage is 0. Okay. So during the overlap period, mu output voltage is 0. So therefore there is a net reduction in the voltage applied to the load. This is due to the source inductance. What happens in the 3-phase case? Will the output voltage is 0 during commutation period? We will see. Assume that case 1 I am just assuming a uncontrolled off wave rectification or rectifier. D1 was conducting, D2 starts conducting at the point of natural commutation. When the Bn becoming more positive than VAN, for some time D1 and D2 starts conducting. Okay, there is a short here. D3 is still open. So what is the KVL for this loop? Is VIN minus VBN is 2 LS I ds by dt is the current that is flowing here. Okay, current increases, this current decreases. Okay, IT. Okay, so output voltage is V0 is equal to VIN minus L dis by dt. So if I substitute here, V0 is found to be VIN plus VBN by 2. So remember, in a 3-phase case, when the two devices are conducting, output voltage is the sum of the two voltages, phase voltages divided by 2. So just see here, at this instant is the point of natural commutation. Prior to this point, this is the load voltage, whatever be, whether it is VAN or BN or CN, doesn't matter. At this instant, both the devices started conducting. Now this voltage is instantaneous value of this plus instantaneous value of this divided by 2. Okay. So, I need to add up these two voltages and divided by 2 will give you the output voltage. I am assuming mu to be 30 degrees. So, at this instant overlap is complete. So, outgoing device turns off completely. Now, the output voltage is corresponding to the instantaneous value of the incoming phase. So, there is a jump. So, though I have used diodes, I should have had a smooth waveform, there is no jump in uncontrolled rectification. Okay. Now, here you find that due to source inductance, there is a reduction in the voltage and this is going to be a jump in the output voltage. Okay. This is for control bridge.